Hi, my name is Sergey Levine, and I'm going to talk about offline reinforcement learning. But let me first start with a big sweeping question. What makes modern machine learning work? I think at the core of modern machine learning is basically the combination of two basic ideas: the ability to use very large and very diverse data sets, and to train very large and highly expressive models like deep neural networks. There's of course a lot more to it than that, but this basic combination is at the heart of modern techniques in computer vision, natural language translation, speech recognition, and many others. Now, what about reinforcement learning? What if we want to autonomously learn skills? Well, reinforcement learning is fundamentally an active learning framework where you have an agent that interacts with the world, collects some data, uses that data to update its policy, and repeats this many, many times. And we've seen this basic recipe succeed in a number of settings, from playing video games to simple robotic tasks to playing board games. But if we want reinforcement learning to really generalize in kind of a comparable way to what we've seen in computer vision, we might need to collect very large data sets every time we update our policy. And we haven't seen the kind of generalization in the world of reinforcement learning that we've seen in things like image recognition and speech translation, the kind of successes in big open world settings. And perhaps the reason for this enormous gulf is that if you want kind of ImageNet level generalization, then you need to collect ImageNet level data sets each time you update your policy. And in an active learning framework, that's simply impractical. So could we instead develop data-driven reinforcement learning methods that can use large and diverse data sets without having to recollect them every time? The standard RL framework is an on-policy framework where you interact with the world using your current policy pi_k and then update that policy to get pi_k plus 1. Off-policy reinforcement learning extends this idea to also store data from all of your past policies in a buffer. Offline reinforcement learning takes this point even further. Offline reinforcement learning is essentially off-policy RL, but with an additional change to the protocol where we don't assume anything about the policy that collected the data, so the data was collected by some behavior policy pi beta, which could have been even a hand-engineered strategy or even a person. That data was stored in a buffer D, and during the training phase we don't interact with the world at all anymore. We're simply going to use that data set to train a policy pi, much like how in supervised learning we would use an existing data set to train a model without having to go out and recollect more data each time we train. Once pi is trained, then it can be deployed. Now, of course, in reality, there's more nuance to this picture. In reality, this data set D, once it can come from any behavior policy, it can also come from any combination of behavior policies. So for instance, if we have an autonomous agent that is interacting with the world, we might take all of the data that is collected in all of its past interactions, pool that data together with any demonstrations and any other sources of experience, use all of that as our offline data set, and if we're not happy with the performance that we're getting, maybe we do a little bit of additional online fine-tuning. And that's probably closer to the formula that we'll really use in practice. But the root problem here that we need to overcome is to enable this kind of offline RL. So once we get offline RL to work, the fine-tuning would be much more straightforward. And of course, if we can get this to happen, we can build very effective policies for robots, but we can also extend RL to other domains where it has traditionally been very difficult to apply because of this active learning paradigm. Things like assisting with medical diagnosis. You don't want a policy to explore by randomly prescribing drugs to patients, but if you can utilize data from humans that have prescribed drugs to patients in the past and do RL on that, then you can actually apply RL to this problem setting. Running scientific experiments, controlling chemical plants, problems in logistics, warehousing, e-commerce, etc. All of these things are settings where it is expensive, difficult, or dangerous to run active data collection, but where offline RL could be tremendously impactful. So in today's talk, I'm going to describe why offline RL is difficult, talk about how we could address some of these challenges, and conclude with a discussion of how we could evaluate offline RL algorithms. So let's start with the challenges. First, a quick primer on off-policy reinforcement learning. So if you have an agent that interacts with the world by selecting actions, the world responds with states and rewards, and the agent's goal is to select a policy pi, which gives a distribution over actions given states, to maximize the expected cumulative reward that the agent will receive. A very useful object for doing this is something called the Q function. The Q function tells you if you start in a particular state and then take a particular action, what is the total reward that you will accumulate. If you can learn a Q function for a given policy pi, then you can get a better policy by taking an action with probability 1 if it maximizes the Q function. This is the basic idea behind policy iteration algorithms. So in policy iteration algorithms, you alternate between computing Q pi and updating pi greedily with respect to Q. And actor-critic algorithms you can think of as a kind of differentiable generalization of this idea. You could also develop direct Q-learning algorithms, where you minimize the difference between the left-hand side and the right-hand side of the optimal Bellman equation, and this can also be shown to yield the optimal policy. So if you find a Q function Q star that satisfies this equation everywhere, then you can recover the optimal policy from that. So this immediately suggests a simple learning algorithm, which is at the core of all Q-learning methods, which is to simply minimize the squared error between the left-hand side and the right-hand side of this equation. And if you see me write Q minus Y, Y is just shorthand for the target value, the right-hand side of the optimal Bellman equation. All right, now the crucial thing about these Q-learning algorithms is that you don't need on-policy data to evaluate the right-hand side of this equation. So you can take any SAS prime tuple, perform the max over A prime, and use that to update your Q function, even if your current policy would never have taken action A in state S. So this suggests kind of a family of off-policy Q-learning algorithms. These are also called fitted Q iteration and so forth, where you collect some data using a given policy. It doesn't have to be the same as your current policy. Add it to your buffer, sample a batch from the buffer, minimize the difference between the left-hand side and the right-hand side of the optimal Bellman equation, and repeat this process. And you could also go out and collect more data if you please. So the visual illustration of this is that you have your environment, you've collected some transitions, placed them in your buffer, you use this buffer for off-policy Q-learning, and you can go out and collect more data if you would like, but if you're doing offline RL, then you would skip this step. So does this basic recipe actually work? Well, a couple of years back, we ran a large-scale deep reinforcement learning experiment where we wanted to evaluate both offline RL and online fine-tuning. So we developed this algorithm called QT-opt, which you can think of as a continuous action generalization of Q-learning, where the max is performed using stochastic optimization, and we ran it on a large-scale robotic learning problem. The resulting policy was used for robotic grasping, and it actually worked really well. So here you're seeing the policy trained with deep RL directly from images being tested on a wide range of different objects that it had never seen before during training. And you can see that it doesn't just pick up objects successfully, it actually exhibits sort of a degree of common sense. When someone perturbs the scene, it reacts intelligently, it retries, regrasps, and so on. So it's actually paying attention to what's going on. And it's generalizing. So we tested it on a large data set of test objects that it had never seen before, and we specifically wanted to understand how does the offline setting compare to the fine-tuning setting. So in the offline setting, we had 580,000 offline grasp attempts collected over several months, and in the fine-tuning setting, we additionally fine-tuned with on-policy data for 28,000 more grasps. That's a very small number, but it was enough to see some difference. The success rate was 87% in the offline phase and 96% with fine-tuning. This might not seem like a big gap, but if we then look at the failure rate, we can see that the failure rate is almost more than three times higher in the fully offline setting where the fine-tuning was not available. So clearly there's a big gap between the purely offline setting and the setting where we also do some on-policy learning, although the offline setting does basically work to some degree. So what's the problem? More recently, we've investigated this question, and this is work done by primarily by two of my students, Avril Kumar and Justin Fu. One hypothesis we had was maybe the problem has something to do with overfitting. Maybe when you have that offline data and you can't collect any more, you'll just overfit to the offline data. So we wanted to see how well we can do with offline training with different numbers of data points using a standard actor-critic algorithm. The algorithm here was soft actor-critic. So you can see here we're varying the data by orders of magnitude, and there's basically no difference. So a good reward on half cheetah would be something around 8 to 10,000, and here we're getting a negative reward. And it doesn't actually improve as we increase the amount of data. So the red line, which has 1 million data points, is about the same as the blue line, which has 1,000. How well does the algorithm think it's doing? Well, it actually thinks it's doing really, really well. So if we plot the Q values, which are its predictions about how well it'll do, you can see they're much larger. And the y-axis here is actually a log scale. So they're not only positive, they're enormous. So it's not overfitting, because more data points doesn't make it do any better, but it is grossly overestimating. Now, another hypothesis we might have is that maybe the training data is just not very good. This hypothesis is not true in this case, because we can behavior clone just the best trajectories in the data set, and we'll do much, much better than this. So there's really something else going on. It's not overfitting, the data is definitely good enough, it's something else. The problem really comes down to distributional shift. So in a nutshell, we can think about distributional shift like this. Let's say that you solve some empirical risk minimization problem, just a standard supervised learning problem, minimize the difference between f of x and y on some data set p of x. And then you want to know, given some x star, is f of x star going to be correct? Well, you know that the expected value of your loss under p of x is going to be low because that's what you trained for. So you might hope that this means that x star is going to be correct. The expected loss under some other distribution p bar of x is not in general going to be low if p bar of x is not equal to p of x, so we know that. But what if x star comes from p of x itself? Is that guaranteed to be correct? In general, the answer really is no, because we're minimizing the expected value of the loss under p of x. We're not minimizing the pointwise loss uniformly at every x. So this is kind of the difference between average error and minimum error. So even though x star might come from p of x, even then you can't guarantee that you'll get it right. The only thing you can really guarantee is that you'll get the right answer in expectation over p of x. Now, we might say that usually we're not really worried about this because, well, neural nets, they generalize pretty well. So while technically you might be a little wrong here and there, usually good generalization will basically save the day. Is that true? Well, often that is actually true. But what if x star is not chosen randomly? What if it's actually intentionally selected to be the argmax of f of x? In that case, actually, even very good function approximators can get really, really messed up. Let me illustrate this with a picture. Let's say this green curve is the true function, and the blue curve is the function you learned. That's your f of x. Now, you might say, well, it's pretty good, like the error is very low everywhere, but if you take the argmax, you basically get that tall peak, which is actually one of the largest errors that this function has. Now, of course, I chose that function that way intentionally, so you might say not all functions will look like this, but in general, in high dimensions, if you take the argmax, you will basically optimize for the largest error that you can get. So what does this have to do with Q-learning? Well, if you look at the form of the right-hand side of the optimal Bellman equation, we can actually rewrite it in a way that makes the distributional shift a bit more apparent. So instead of writing it as a max, let's write it as an expected value under pi nu, where pi nu assigns a probability of 1 to the argmax. It's exactly the same equation, it's just written differently with an expectation now. So this right-hand side, that's your y, that's your target value. And then you could say, well, how is Q trained? What is its objective? Its objective is to minimize the expected value of the loss under some distribution pi beta. So that p of x now is pi beta of s. So that means that you will have a low loss on other SA tuples sampled from pi beta, because you'll fit the target value accurately there. So you'd expect good accuracy when pi beta is equal to pi nu. But how often does that happen? You're not trying to copy the behavior policy, you're actually trying to do better. So the whole point of doing RL is to make pi nu be different than pi beta. So when you do this, of course, your target values will become incorrect because of distributional shift between pi beta and pi nu. Even worse, the way that you actually select pi nu is by maximizing the Q values. And remember from the previous slide, if we pick the input by taking an argmax, we're going to get ourselves into a lot of trouble. And that's why the Q function thinks it's doing a lot better than it actually is. Because we're selecting those values for which the Q function essentially makes the largest errors in the positive direction. All right, so how do prior methods try to address this problem? Well, one thing you could do is you could devise an actor-critic algorithm where the critic is updated like before in expectation under pi nu, but the actor is updated with some constraint that constrains the distributional shift directly, limits how far pi can move away from pi beta. And then you repeat this process. Now, in principle, this should solve distributional shift, right? So it'll limit how far pi is from pi beta, and you'll have no more erroneous values. This is at the core of what we call policy constraint methods. So we have a tutorial that we wrote on offline RL, which is referenced here at the bottom of the slide, that catalogs these techniques. And this is a large class of algorithms that we would call policy constraint methods. It's a very old idea. In fact, it's so old that I don't even know whether it has a name. It's popped up time and time again in the literature on linearly solvable MDPs, KL divergence control, trust regions, covariant policy gradient, natural policy gradient, and so on. And more recently, it's been used in a number of recent papers, many of them focusing on KL divergence constraints, but also a few others. There are a few basic issues with this class of approaches. One is it can be way too conservative. To see why this might be the case, imagine that pi beta is random. A KL divergence constraint will essentially limit how far you can move away from being random, which is a really big problem. We addressed this in a paper that we wrote in 2019. This is a paper led by Avril Kumar, which proposed an algorithm called BEAR, which uses a kind of an MMD constraint to approximate a support constraint. So instead of limiting KL divergence, you could bound the support. A second issue is that estimating the behavior policy in order to enforce that constraint can actually itself be very difficult. This is a plot from a recent paper written by Ashwin Nair and colleagues called Advantage Weighted Actor Critic. The paper actually studies fine-tuning after offline RL, but one of the plots here shows the log likelihood of the estimate of pi beta as more and more data from varied policies is mixed into the buffer. And you can see that the log likelihood drops precipitously. So estimating the behavior policy can be very difficult, especially when the behavior policy doesn't come from RL, when it comes from a person or some non-Markovian source like a hand-engineered behavior. Now, we could actually avoid this issue to a degree using implicit constraints. So this is a little bit of an aside to this talk, but we can actually address issue 2. And the way that we can address it is by noting that this constraint optimization problem actually does have a closed-form solution, which we can derive using Lagrangian duality. It's not a solution that we can compute exactly, but if you basically write out the Lagrangian of this problem and solve for the optimum, you'll get this expression in terms of a dual variable lambda. Here, A, the advantage estimator, comes from your critic. And this idea has popped up in a number of previous works, some of which are mentioned here. But the cool thing about this closed-form solution is you can approximate it via weighted maximum likelihood. So you can see that the expression for pi star involves multiplying pi beta by a bunch of numbers. So to estimate this, you can actually take the expected value under pi beta of log pi times those numbers, where the expectation is computed by taking samples from the data set. So essentially the pi beta term, it looks like it just disappeared, but it hasn't disappeared. It's actually inside the expectation. But importantly, this means that you can estimate this expectation using only samples from pi beta without actually knowing what pi beta is, which means that you can avoid estimating pi beta explicitly. And then you can use the critic to get the advantage values. So this is the idea behind two algorithms that we've developed, advantage-weighted regression and an algorithm called advantage-weighted actor critic, which appears in this paper called Accelerating Online Reinforcement Learning with Offline Datasets. This method does not require estimating the behavior policy, and it works very well in the offline RL setting. But maybe we can solve the overestimation problem at its root. Maybe instead of coming up with better ways to constrain the policy, we can simply prevent the Q function from overestimating. And this is the idea that I'm going to talk about in the second part of today's talk, where I'll discuss a new algorithm I've developed called conservative Q learning. So let's come back to those Q errors. Remember that we're overestimating very badly, and the reason we're overestimating badly is that the max in Q learning basically finds the largest positive error. So what if we try to explicitly avoid this? What if we construct a modified objective where we have our usual Bellman error minimization and a second term that tries to push down on the big Q values? Basically, the second term minimizes the Q value under some other distribution mu, where mu is chosen to maximize Q values. So mu basically finds the large, tall peaks, and the objective minimizes the Q value at those peaks explicitly. It turns out that you can prove that Q hat pi is less than or equal to Q pi, meaning that it's less than or equal to the true Q function for pi if alpha is large enough. And that's really nice because that means that if you choose a large enough alpha, you will not overestimate. So this is an algorithm developed primarily by Avril Kumar, and the idea is very simple. You're going to learn your Q hat pi, which is a lower bound on the true Q function for a policy pi, and then you will update your policy to take the argmax of the expected value of Q hat pi under that policy, and repeat this process. Now, because you have a bound at every step, you're guaranteed not to overestimate, which means that you'll take a policy that sort of conservatively optimizes for the best value of the worst Q function. Now, you can actually construct a much better bound. Instead of simply minimizing the Q value under mu, you could additionally maximize the Q value under the data. So simply minimizing the Q value under mu will push down Q values, which means that you will systematically overestimate in all cases. You'll basically never get the right answer. But if you also maximize the Q value under the data, if you push up on the samples from the data set, this has the interesting property that if your mu is equal to the data distribution, then the regularizer has no effect. But as the high values deviate from the data, you'll push them down more and more. This will cause you to underestimate a lot less. Now, you're no longer guaranteed to have a pointwise bound. You're no longer guaranteed that Q hat is less than or equal, that Q hat is less than or equal to Q at all SA tuples. But you can still show that there's a guarantee that the expected value of Q hat for your policy is less than or equal to the expected value of the true Q function at all the states. So if you're really only concerned with improving or evaluating a policy, it turns out that this still gives you a bound. So in summary, the conservative Q-learning algorithm works very similarly to regular Q-learning or regular actor-critic methods, except that when it computes the Q function, it minimizes the big Q values and pushes up on the Q values in the data. The full result for the theorem that shows the lower bound is written here. So V hat is the expected value of the estimated Q function, and V is the true value. And V hat bounds V with a looseness term determined by the regularizer. So this term is always positive and it's multiplied by alpha, so this is your pessimism. And it also has an error term that accounts for sampling error, which depends on a concentration constant. This is basically a constant that represents how closely you've arrived at the true solution based on the number of samples you've collected. So if you choose alpha to be large enough, the negative term can sort of overwhelm the positive term, and you're guaranteed to have a bound. Of course, the correct choice for alpha depends on some quantities that are very difficult to compute in practice, so in practice we would select it heuristically, but we can test empirically whether this actually results in a bound. So what we're going to print next is underestimation versus overestimation on some benchmark tasks. So specifically, we'll actually write out the expected value of the learned Q function, Q hat, minus the true expected value, which is obtained by a Monte Carlo estimation. So here you can see two versions of CQL. The first one uses both the minimization and the maximization term. The second one just has the minimization term. And then a number of baselines. Ensemble methods with 2, 4, 10, and 20 models in the ensemble, and Bayer, which is the support matching method that I mentioned in the previous section. Here, negative values mean that the Q function is underestimating. Positive values means that it's overestimating. And you can see that CQL always has negative errors, which means that it always underestimates. It never overestimates the true Q value. And in particular, the more sophisticated bound is much tighter than the pointwise bound. The other methods all have positive errors, and the ensembles in particular really don't estimate the bound very well. So the ensembles, despite being pessimistic with respect to their uncertainty, they all wildly overestimate. So if you really want conservative Q values, if you want lower bounds on the true Q, don't use ensembles. It's not going to work. Bayer overestimates much less, but it's still quite optimistic. All right, but before I tell you how well CQL really works, I want to talk a little bit about how we can evaluate offline RL methods. So remember that in offline RL, we can use any behavior policy pi beta to collect our data. So if we just want to do some benchmarking, one thing we could consider doing is just training a reference policy with regular RL. That seems like a really simple choice. So a typical protocol used in prior work is to train pi beta with online RL, and then either collect data throughout training, or even worse, just take data from the final optimal policy. I'm going to claim that this is a really bad idea, that this is a really, really bad way to evaluate offline reinforcement learning algorithms. We really just shouldn't do this. Because if you already have a good policy, why are you doing offline reinforcement learning? Why not just use your good policy to solve the task? In the real world, your data might not come from an RL policy, it might come from non-Markovian policies that can't be represented with any neural network. So if your method relies on estimating pi beta, you're basically deluding yourself if you're using RL to generate your data, because you might not be able to represent the true policy in the real world. It might come from human users or hand-engineered behaviors. So methods that don't estimate pi beta will do a lot better, but your evaluation protocol will not show you that if you use RL data. You have to use data that's representative of real-world settings, and also data that leaves room for improvement in the sense that it should be possible to do much better than pi beta. Offline RL has to be able to learn policies that are much better than the behavior policy, otherwise there isn't really any point in using it. So without testing for these properties, we really can't trust that we're evaluating our offline RL methods properly. To address this, we've developed a set of benchmarks called Datasets for Data-Driven Deep RL, or D4RL. This is work led by my students Justin Fu and Avril Kumar. And I would really highly recommend using these benchmarks because I think they evaluate the properties that really matter for offline reinforcement learning. And increasingly, D4RL is becoming a kind of de facto standard for evaluating offline RL methods. So what are some important principles to keep in mind for generating the data? One principle is that you should make sure to include data from non-RL policies, including data from humans. So one of the things we made sure of in D4RL is to include behaviors where the behavior policy is not an RL policy. So for example, we included a data set based on the dexterous manipulation tasks proposed by Rajeswaran and colleagues that actually used human data from a data glove to generate the data. Another principle is that you should make sure that offline RL can do much better than the behavior policy. One way in which it could do much better is by stitching using dynamic programming. So if you've seen a behavior that goes from A to B and another behavior that goes from B to C, offline RL should be able to figure out that it's possible to go from A to C. And we've included a set of navigation tasks that emphasize this principle, simple tasks based on 2D navigation, and more complex tasks that involve navigating using a kind of an ant robot. And in both of these cases, the goal for offline RL is to learn a behavior that moves from one point to another without ever having seen that full trajectory in the dataset, but by restitching other trajectories that were seen. Here's a visualization of all the training data for the AND task. And lastly, we should make sure to include realistic tasks. So we made sure to include image-based tasks for autonomous driving based on the Carlos simulator, dexterous manipulation tasks for multitask settings with the Franka robot based on this kitchen environment proposed in the Relay Policies paper by Abhishek Gupta, and a traffic control simulation environment developed by Professor Alex Bynes' lab, which requires an autonomous vehicle to modulate the flow of traffic. So the tasks in D4RL involve the standard Mujoka benchmark tasks, which previous papers have used, including the standard expert, medium, and random datasets produced by Avril Kumar in the Bayer paper, as well as some additional mixed datasets that are much more difficult. It includes these mazes, both 2D and ant mazes, to evaluate stitching. It proposes datasets with human data for both dexterous manipulation and whole arm manipulation, and more realistic tasks based on controlling traffic flow and autonomous driving in Carla. So how does CQL compare to prior methods on these tasks? So here are some previous methods. For the ant maze tasks that require stitching, essentially no previous methods work. Everything gets a value of almost 0. And we might wonder whether it's possible for anything to work on these tasks at all. We'll see the answer to that in a second. A very strong baseline for all prior methods turned out to be behavior cloning, simply copying the behavior policy. So for most of the tasks that involve human data, just copying the data actually worked better than previous offline RL methods. In comparison, CQL actually does very well. So for the tasks with human data, it does up to 5 times better than the next best method, which in many cases is actually behavior cloning, 1.5 to 3x better with only the demos, up to 5x better if it's augmented with cloned data. The pen task is the easiest of the tasks, the other 3 are much, much harder. For the kitchen task, CQL is the only method that outperforms behavior cloning, and it does so by a considerable margin, 10 to 30%. And on the ant maze task, CQL is essentially infinitely better than all prior methods because it's the only thing that works, reaching as much as half of maximum performance in some cases. So these are percentages, so 50 is half. We also evaluated CQL on a difficult Atari task proposed by Agrawal et al., where we used the smallest dataset, the 1% dataset, and we saw enormous improvement over all prior methods, so 1.5 to 6x better. So in summary, CQL is an offline RL method that actually really seems to work. In fact, on these harder tasks, arguably the previous methods don't really work because they don't outperform behavior cloning. CQL really does seem to work. And we seem to actually know why it works, because of the lower bound property. But of course, there's still plenty of room for improvement. So these scores are all normalized, with 100 being the largest. And we can clearly see that CQL is very far from the largest return, so there's plenty of work left to do. All right, so a few closing remarks. Offline RL is quite difficult, but it also has enormous promise, and initial results suggest that it can be extremely powerful, as we saw from some of the robotics results. We need to think carefully about how to evaluate offline RL methods, and if we can learn a lower bound Q function, like in CQL, we can substantially improve offline RL performance. All right, thank you very much for listening.